what density is, right? Density is when what? What is the formula for density? Mass over volume, right? So basically bulk density is, again, remember that 1 liter container with coir peat, so that is 1 liter volume, right? But then you weigh all of that peat, that's the weight of the peat. So let's say you have a container 1 liter in volume, you fill that container with coir or peat, whatever that substrate is. So the volume is 1 liter because you fill it all the way to 1 liter, but then after that you take that coir or peat and weigh it on a scale, you get some weight in grams. So that is the weight of the peat and the volume is 1 liter. So then bulk density is measured as weight over volume, right? So the weight divided by 1 liter, that's what grams per centimeter cube. That's bulk density. Now, what do you think? Which will the soilless substrate or a regular soil will have higher bulk density? Which one will have higher bulk density? Will a soilless substrate or a regular soil have higher bulk density? Why? Because regular soil weighs more. For a given volume, the weight of regular soil is much more than soilless substrate. One of the biggest advantages of soilless substrate is get the low bulk density. So you can do that calculation very easy, right? We also learned about porosity and pore space, right? Percentage porosity, things like that. Pretty simple calculations. Okay. You know container capacity? We talked about it. Saturation, container capacity, wilting point. So there is something about container capacity. And then you can also calculate air space and water space in a soilless substrate. So these are all some concepts. So in this laboratory, you will learn how to estimate several physical properties of commercially available soilless substrate. So for that, normally what we will do is we will give our students actually some soilless substrates, peat, coir and different things, kind of mix them different ratios, and we'll ask them to actually do this in the greenhouse. Unfortunately, I don't have access here for all those things. So I'm going to start with some numbers for you. All you need to do is, you see here there is a characteristic weight of empty container 25 grams. Okay. I want you to go through this table. I put some comments also, for example. Okay. Weight of container plus substrate is W2. That's 55 grams. Okay. But if you follow this, it's a pretty simple thing. You can calculate a lot of things on this chart. When you get to the end here, you have to make all those calculations. But that's why I was asking if you can see it from there, because I can probably. How about now? Can you see it? Can you read and see it from here? Or what you can probably do is come over here, take a picture, and then if you have a phone, you can work on a piece of paper. Either way is fine. Or maybe come close by. But this table is important. I'm providing what information on how to calculate on the comments column. Okay, just go through this. You see these numbers I gave you. These are things usually students measure, but I don't have, like I said, access to substrates or media here. So I'm already putting those numbers for you, but you can use those base numbers and complete the rest of the calculations. Okay, so for example, here number 5 is bulk density, right? So I'm saying bulk density number 4 divided by number 3. What is number 4? Weight of dry substrate divided by number 3 is what? Volume of container. So you have volume of container is 1000. How do you get weight of the dry substrate? I'm telling you here, W2 minus W1. So it is right there. If you just read through it carefully, you will find everything you need there. It only takes probably 15-20 minutes to finish that. But you can calculate all the characteristics, and let's finish this table. So if you can see from there at the back, I will leave it here, but if you can't, I would say take a picture from your phone and have it in front of you, and you may have to use a paper and a pen and calculate all these things, wherever these empty cells are there. This is all the places where you're going to make some calculations based on the information in the comments column. Okay, just start doing it. Why don't you come even closer if you want to take a better picture, and just go through that slowly. and you will get experience with how each of these things can be calculated. It would have been nice if there is some media here, and so you can actually weigh and add some water and then weigh it, but I don't have access, sorry. Okay. I want all of you to finish these calculations on a piece of paper, and when you're done, just let me know. Okay, there is one more activity of this, but we'll discuss once you're done. You understand, right? What I'm saying? It's pretty simple, very easy. Read through the comments column. In the comments column, I mentioned everything, and have a paper and pen and start working on it. हम आज वो physical characteristics activity कर रहे हैं. So we have the information right on the table, and if you just read through the comments, you can calculate all. So there are already some data input into the table, but there are a lot of empty cells. If you look at the value column, there are empty cells. That's what you're going to calculate. But you can read through the comments and calculate them back. But that gives you an idea about how to calculate several physical properties. And when you are done, we'll review everything one at a time, slowly, and we'll go through everything. But try to read and get some idea about it. Some of the comments are for actually students to work. So for example, you see the second comment, compact the substrate gently in the container. That's because this is actually done by students. We'll give them parts and we'll give them substrate. We'll ask them to put the media in the substrate, compact it. But you don't have to worry about it. But then some of them are formulae that you have to really look into. Okay. Yeah. Volume of solids in the substrate. Number 3 minus number 8, right? So volume of container is number 3. So again, uh, what is in the, so that's important question. What is in that container? It has got solids, it has got pores inside. Then you fill the soil all the way to the top, right? So once you know the pore space and once you know the total volume, you subtract pore space from the total volume, what is left over is solids. Is that the question you asked me? 8 minus, what did I say here? 8 minus, oh, you shifted it. Okay. Yeah. Okay, good. Good catch. Do it the other way. Yeah. 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 Sure, sure, please. So I want all of you to pay attention to me. Can you? It is 3 minus 8. That is correct. However, I made a typo with the numbers. Okay. Again, keep in mind, I just made up numbers. I did not weigh at anything like a real substrate. I think the problem is that volume of the container. It's shown as 1000. Please change that to 3000 and everything will be correct. Now, the formula 3 minus 8 for volume of solids, that is correct. It's just that I had a wrong number typed in there for, so make that to 3000 and I think everything will flow well for after that. So right here, I'll probably change that. Um, so this one, right? Change this to 3000. So if that is 3000, um, then you get a positive number here. Okay. I just want to make it a bigger container. That's it. Okay. So let me know when you are done so we can start filling up this table. Okay. And then we can discuss each of those carefully. Okay, let's talk about number 6, bulk density. Is that formula correct there? Or, so bulk density, what am I saying? Divide 4 by 3. It should be 3 by 4, isn't it? Right? Come on. So this formula, where is that? Bulk density is, number 4 is volume, mass per unit volume, right? What is mass is what? 3. Yeah. This is, this is different. Oh, I got confused with this column. Okay. Correct. I got it. I don't know where this came from. Huh? Oh, it came there. But anyways, don't follow these numbers. Okay, this I'm talking about numbers in here. Okay, I don't know what these numbers are. Okay. Oh, so while that comes up, so did everybody finish bulk density? Right, it's very easy, right? So how much weight did you get for the soil? What is the weight of dry soil? 30 grams divided by 3000 grams per centimeter cube. It's a very small number because it's pretty light medium. Okay. What was the next one? Somebody took pictures, right, on their phone. So what's the next calculation? Weight of water added to reach saturation. Okay. So I want to now think, why am I trying to bring the substrate to saturation to find pore space, total pore space? What does saturation means? Saturation means all pores are filled with water, right? So now if I bring the part to saturation and measure the volume of water, then that is total pore space. That's the easiest way to do that. All you need to do is take a part, cover the part with some plastic paper, okay? Because if there are holes, the water will drain out. But put them substrate, and then first put the plastic paper, fill it with the substrate, keep on adding water until you see the water actually starts appearing at the top of the substrate. There is no more water you can add, right? That's like all the pores are filled. At this time, puncture that plastic from bottom, the water will drain into a container. Measure all that water. You will get in milliliters or in centimeter cube. That is the total pore space. That is the easiest way to determine total pore space of a substrate. Okay, does it make sense? The poured one will be air space, right? Like after draining. After draining, but I'm now talking about I'm not talking about container capacity. I'm talking about saturation. So let's take a pot. Okay, let's begin again. We have a pot, 3000 liter pot. I want to put a liner. I want to put some plastic inside so the water won't trickle out. Okay, and then I want to add substrate all the way to the top, and then I'm taking now water, slowly pouring water, and it might take, I don't know, several times, but at some point I will start seeing that the water is actually seen on the surface. Tiny film is there. What that means is that all the pores are filled, and if you apply water, it's only going to overflow. But right at that point, when you start seeing that shiny film of water, stop adding water. At this stage, all pores are filled with water. There is no airspace at all. Everything is filled with water. All you need to now do is take a pin or something, puncture hole at the bottom of the pot. When you puncture hole, what happens? The water will release, and then you collect that water into another beaker or something, and you measure the volume. All the water comes out, and well, actually, you don't need to even puncture it. If you know how much you're applying, then that's also enough. But after you puncture, what happens? The macropores drain, and then whatever you measure is you're right, airspace. And then whatever you're pouring is the total pore space. Whatever you are measuring is the airspace, and what is left over is the container capacity. Three simple things right there. Does it make sense? So pour all the way to the top, but measure how much you're pouring. Whatever volume you pour is the total pore space. Make a hole, collect the water at the bottom. Whatever comes down is macro pore space. That's air space. So you get air space, and that number minus what you poured is what is left in the pot, which is the container capacity. Those are the three ways you can determine all those three very easily. Once you know that, they convert them into percentages, right? So I'm going to open this. I have to check now the formula I typed there. I think you're right.
Weight of container at saturation minus weight of substance plus substrate.
What is that for? What formula is that?
For calculating this one, weight of water added to reach saturation.
Okay, so let's see that. I probably can see it here. We'll go through the calculations on this board so you can all see. Okay, so we're changing this, right, to 3000. Okay, let's do the math. So weight of dry substrate is 30 grams, right? Okay. All right, then bulk density is 30 grams divided by 3000, and we got what? 0, 0.01 grams per centimeter cube.
So 0.01.
Is that right? 0.01. Everybody got that number? 0.0. It's easy. All right, next, weight of container at saturation. Add water in small volumes until a thin layer is seen at the top. Okay, so that's 1600 grams. Okay, weight of water added to reach saturation is W3 minus W2, which is what? 1600 minus T5, which comes to
1545.
15. Okay. Now, normally the way it is done is the substrate right here is a dry substrate, meaning there is no water in it, right? So you can measure how much water you're adding, or you can also weigh it for more accuracy. Still it is the same number, right? You must have added 1545 ml to get it to saturation, but we are getting the same number by weight here, that's all. So you start with a dry substrate, you keep on adding up to saturation, and then you subtract W3 minus W2, you get that is the volume of water added, right? It's very similar. You can keep on measuring every time as you're adding and then record that number, or you don't want, if you don't want to do that, because you're starting with dry substrate, you keep on adding until a film is seen at the top, then get the weight. The difference between W3 minus W2 is the amount of water you applied, right? That is kind of more accurate because it's a weight and you're going all the way to 1 or 2 decimals. So that's the reason why we have 1545 grams. So now that can be converted into, yeah, milliliters, right? Does it make sense up to this point? So we're saying that this is the total pore space, right? Because it's the volume of water we added all the way, and then we weighted it, so it's the pores, total pore space. Any doubt on this one, how I calculate the pore space? Is it good so far? Okay. Then we want to determine volume of solids, and this is where something went wrong, right? So what am I saying here? 3 minus 8. So 3 is volume of container, 8 is pore space. So you have a container, the container has substrate. So in that substrate you have solids and pore space. You know the volume of container, you know the pore space. So to get to solids, you will just get the subtract this from that, right? Minus 1545. So what is that number? 1455 ml or centimeter. That's the volume of solids. Okay. So far good, everybody. All right. Then I'm probably stuck here. Any case, so then what we want to do is volume of water collected after punching holes at the bottom of the container or airspace, right? That's what it is. So this is the amount of water we collected after punching holes. So and then weight of container after completing drainages. So does these things match now? Give me a second. So what was this number? I can't get there. I may have to go back. Yeah, you have to go back. Let's not say. You have to exit. Yeah. Well, save. Okay, save. Where do you want to save? I don't know where it is saving. Okay. So somebody remind me, where are we? We were here, right? Somewhere. Right. So now let's continue the calculation. From, I think we were here, right? 150 airspace. Come on. So now what are we calculating? We want to now calculate weight of container after complete drainage. W4 is 1450 grams. So weight of water in the container after complete drainage is W4 minus W2. What was that number? Yeah. 1395. So 1395 is the water that is held after drainage. After drainage. So that's at container capacity. So that so 1395 is container capacity, and that's water space, and 150 is air space. right? Once you get to there, then everything is expressing as percentage of container volume down here. So I think you can easily finish it, Rao, right? See, if you've gotten up to here, these things are basically you take these numbers and express as percent container volume. Container volume is 3000. So divide that number by 3000 and multiply by 100 to get percentage. So express everything as container volume. All four values you'll get here. Volume of solids, total pore space, air space, and water space, you probably should get this percentages. Let's see what that number, if that number adds to 100 or not. So once you are done, let's review this. So these are the four values I'm interested in, and I want to review one more time how we got all of them. So what are these percentages? Volume of solids, what's the percentage? How about pore space? So those two should be 100%, right? When you add, okay, what is airspace? Airspace, again, airspace, read this, express as percent of pore space, not part volume. Remember that. See, these two are expressed as container volume. These two are expressed as total pore space. Okay, so what is the pore space? Air, that's airspace, right? Right, and the water is remaining. Okay, okay. Let's wait for everyone to finish that. So in real world, I'm going to put this back. Well, let's give everybody another 5 minutes to finish this. So, has everybody completed? Who needs more time? Please raise your hands. If you need more time, it's okay. We'll give you some more time. Please raise your hands if you have not completed. You need some more time. Okay, one here. How about you? Do you need more time at the back? Do you need some time? Are you done? You're done. You're done too. How about you? You're done. Okay, we'll wait for Prakash. Good. So now let's go back and look at this table. I want all of you to pay attention to what I'm saying. This is this table is real world situation. Okay. So let's say you buy some medium. You have no clue about the physical properties of the medium. The company guy does not tell you anything about it. They say, sir, we don't do anything like that. All we know is it has got peat in it, it has got vermiculite in it, or it has got some perlite in it. That's it. Right? But bulk density, porosity, airspace, water space, they're all important. They're functional components. They affect plant growth. So you need to know. So what you can do is, all right, I'm not going to buy a big bulk lot from you. Probably I'm going to take a small bag, okay, and I'm going to do my own testing. I'm going to do my own testing. So you can just get a small bag, come back to your greenhouse, you take a pot, okay, and then we start measuring these things. So first thing what we want to measure is bulk density. We want to make sure that it is light in weight, okay, good. But then comes the real ones. Of course, you want to know total pore space. Remember the first slide I have shown you, the pore space should be 75% in soilless substrates, whereas in regular soils it is only 50%. So you want to know how much is the total pore space. That pore space is the functional component of a soilless substrate. The more, the better it is. And the company guy is not telling you. So how do you measure the total pore space? Simply by putting a lining material and adding all the way up to the top with the substrate, whatever you got. Also gently compact it. Compact it the way you would normally compact your pots. Okay, not too much or not too little. If you are going to grow plants in the pot, you're going to do some compaction, isn't it? Just do that same way. And then apply water all the way until you see the thin film. Now you know that you have filled the entire pot, all the pores with water. Okay. If you have started with a really dry substrate and then now you punch a hole, all of that water that comes out is airspace. But then before you do that, you have to weigh the pot, right? So you have a pot, you have substrate in it, and let's say it's 100 grams dry substrate. You kept on adding water, and now it is 1600 grams. So how much water did you add? Well, originally 100 grams. Now it is 1600 grams. So you added 1500 grams of water. 1500 grams is equals to 1500 milliliters. That is the amount of water you added. 1500 milliliters is the pore space. 1500 centimeter cube is the pore space. If the container is 3000 ml and you added 1500 to get to saturation, that means pore space is only 50% in that medium. Right there you have determined it. Although that company guy did not give you, you are actually able to calculate in your greenhouse. Same way you can calculate container capacity, air space, and all other things based on this table. So this table will really help you. I put some numbers there because I couldn't do it before I came here. But in reality, the entire table, the value column will be blank for you. It's completely blank. You have to fill up for your situation. You start filling up one at a time, then you come all the way to the end. Now you got all the physical properties of the substrate you want to buy. So let's say you get the substrate from 2 or 3 companies, different substrates, right? You get from different companies and you do the same calculation and you get the numbers from different companies. You know, what is the total pore space, what is the container capacity, those are the two things. You want to buy the substrate that has got the highest container capacity, highest pore space, those two things. So now you are actually doing your own research. All you need is a pot and substrate and this table. Simple calculations. That gives you the data that you will need to choose one substrate or the other. Right? In the market, there are so many companies, right? Everybody wants to sell you their product. But how do you know which one's the best? This table. Using this table, you can identify whether substrate 1 or substrate 2 has highest container capacity or whether substrate 1 or 2 has the highest pore space. You want to make sure you buy the substrate which has got the highest pore space and highest container capacity, because pore space is the functional component. More pore space, more water, more nutrients in the substrate, so that your plants get bigger. That is the advantage of this table. That is the advantage of these simple calculations. I plugged in some numbers and that kind of confused you. That's simply because I didn't have the substrate. I was writing down some numbers before I came here. But remember that value column, that entire column will be blank for you. You start with an empty sheet and you fill up your own data. Okay. In fact, you can try this even at some point of time, because there's a lot of substrate and parts available in these greenhouses. And if you want to play with this, it's very easy, but it gives you very, very good information. This is how you distinguish one product versus another product. Not blindly, not based on somebody what they said, but based on the data that you generated. You have a lot more confidence in what you have generated, not from what others have generated, right? So that's the advantage of that. Any doubts on this? This is a very applicable table, and you get all of this material. I'm asking Dr. Ashutosh Singh to send you the PDFs. He has already sent it. Did he? Are you going to send them? Yeah, please send them as soon as you can. So they actually have all of this information. So it is there with you at any time. So just remember those numbers are, just write it down somewhere that they are just dummy numbers I put there. But when you actually do your own, just use that and it will be very, very useful to you. Okay? That's activity 1. Any doubts on activity 1? All good? Before we go to activity 2, we have one more activity. Okay. Okay, second one is maybe easy. We'll see. I don't know what's going on. All right, here we are, activity 2. Remember this graph in the class, right? Remember this graph. Now we are going to put this graph to practical use. Okay, whatever I'm teaching you, they all have some practical values. Let's put this to practical use. Read the question. The following is a soil moisture retention curve for a 1000 milliliters of soilless substrate filled in a pot. Okay, using the curve, predict the approximate values of volume of water at container capacity, wilting point, and volumes of plant available and unavailable water. All right, now there are 4 things here. First of all, you need to know, before you attempt doing anything, you need to understand what is container capacity, right? So who can tell me what is container capacity? Okay, go ahead.
So container capacity is the point where the macropores are filled with air and the micro and mesopores are filled with water.
Right, so that's the maximum water holding capacity, right? So that's container capacity. Then what is wilting point? Someone else, not you, someone else. Who else can define wilting point for me? Yeah, you are all about wilting. Go ahead. So there is only hygroscopic water, right? Hygroscopic water, and the plants will start showing wilting. You see that plant is showing already wilting. That's what it means, wilting. Okay, so that's wilting point. Got it. Then what is available water? How do you get available water? What is the formula? You go ahead. Why don't you tell me? You know that answer. What is the formula for available water? It is something minus something, right? It doesn't mean anything. What do you subtract from what? Container capacity minus wilting point is available water. And what is unavailable water? How much, the amount of water at wilting point. Alright, so now you know all the 4 definitions. Alright, now we need to keep those definitions in mind. We have to look at this graph now and understand the graph. Alright. Notice this line is becoming what? Flat, right? It's not going down or up, it's becoming flat. What does that mean? No more change in the water content. No more change in the water content. So the media has dried down, but afterwards there is not much of a change. That means that is wilting point. That is hygroscopic water. Whatever the regular, normally available water, it's all drained out up to this point, and afterwards it's all flat line. So for all theoretical purposes, you know that minus 1.5 megapascals, it is considered as wilting point. It is considered as wilting point. So that is wilting point. Okay, remember that. Second thing, what are the units of this y-axis? Percentage. Percentage of what? What is the container volume? 1000 ml. Remember that. So if I say, I'm just giving you how to calculate wilting point here, but you can calculate rest of the things. What is wilting point? What did I say? Wilting point is at 1.5 megapascals, right? You draw a straight line that is kind of what? 9 or 10, right? So 9% of what?
1000
What is that number? 90 ml. So wilting point is at, how much water is there at wilting point? Okay, now did everybody understand what I said? If you have doubt, please raise your hands, because this is exactly how you will calculate other things too. Anybody has a doubt? Do you have a doubt? Do you understand? All of you? How about that side? Do you understand? Or do you want me to explain one more time? I can explain one more time too. So let me explain one more time, all right, for the sake of everybody. Notice this line. This line is not changing. Meaning, what is this line? This is y-axis is water content, volumetric water content. The volumetric water content is not changing. The pressure is decreasing, 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 negative, but then this is remaining flat. You will see such a response when you are near wilting point. And that's the reason why in plant physiology, we call minus 1.5 megapascals pressure as wilting point in soils or in soilless substrate. So that is wilting point, right at that point. So how much water is there at wilting point? For that, what you do is, I'm going to actually draw it with a pen so you all can see. So I'm saying that this is wilting point, okay? Minus 1.5 megapascals. Now I'm trying to figure out how much water is there. For that, I draw a line like this and I take another straight line like that. It's not a straight line, but line like that. So that number comes close to 10%. So at wilting point, there is 10% water in that substrate. 10% of what? 10% of 1000 ml. 10% of 1000 ml is 100 ml. That's how I figured out amount of water at wilting point. Okay. Now, that's good. Now tell me, what is container capacity? Where is container capacity on this graph? It is way at the top there, right? That's the maximum amount of water. That's all it can hold. Right there, that line is touching y-axis. So that's the maximum amount of water it can hold. So now calculate container capacity, now calculate rest of the things. It's piece of cake, very easy. Okay, you probably have completed it. Go ahead, calculate container capacity. What is container capacity? 50% of, and then afterwards do available, unavailable water and everything. That's pretty straightforward. See the value of that graph. This graph can now tell you actually how much is container capacity, even tell you what is wilting point also. So once you know that number, 100 ml is wilting point, now you know, wow, when the water is 100 ml in the pot, then the plants are going to wilt. You can actually weigh the pot and say if it is 100 ml or not. So you kind of know when the plants will wilt also. Pretty close to that. That's the value of that. And you can now say how much is available water, right? That is, this is the available water, right? That's available water. And you want to buy a substrate which has got lot of available water. That is the value of this graph. Now this graph is also telling you how much water the substrate can hold, how much is available water, and you want to make sure that this is the smallest number, unavailable water. Okay, you want to keep that small. This makes sense to all of you. These type of scientific data, tables and graphs can be put into use for real situations, real world situations. And it is so important that you use this type of data, because you don't want to simply depend on a company manufacturer. Especially if you are investing a lot of money, you don't want to take any risks. You want to be able to generate your own data, and from that data you come up with your own answers. You want to buy a substrate, it's got highest pore space. You want to buy a substrate which got a lot of container capacity. In fact, 50 is very small. In real world, soilless substrate should have 60 to 70% container capacity. Okay, you want to buy a substrate which got really high container capacity and also really less amount of unavailable water. So you give a lot of water to plants, make that available to plants. Those are the kind of things you can extract from these graphs. So this morning we learned about all the concepts. This afternoon what you're doing is you are actually plugging in some numbers and creating some sort of data for yourselves. But more importantly, you are taking with you a couple of applications here, a table and a graph that can actually be used to determine which substrate is better over the other substrate. Any doubt on this graph? All good? Okay. We got 1 hour left, right? We've pretty much finished. Any questions from morning before we adjourn? I have plenty of time. I can sit here and talk to you also, but if you have any questions, go around water, soilless, substrates, components. If you have missed something, take 5 minutes and ask me questions so I want to make sure that all those concepts are clear before moving on to the next one. It's a very rapid pace, right? Every day a new chapter. So after some time, it's all going up here. So we have to make sure that we save the data in our minds, permanent saving, right? Permanent hard drives. Any questions about this? Now, I probably won't tell you how to do this, but I will mention this. They will use graphs like this. This graph is showing relationship between water content and water potential. They use graphs like this, and from that graph you can also estimate how much macropores are there, how much volume of micropores are there, and how much volume of mesopores are there. That's called pore fraction analysis. It's a little bit an extra step. You can really analyze. So when you create a graph like this, everything is possible. You can get everything about the substrate. No more lying, no more hiding. You have everything in front of you. This moisture retention curves. Then comes the question, so how do I get this graph, right? It's nice graph, but how do I get this graph? Volumetric water content. That's easy, right? Let's do an example for volumetric water content, because that's something we thought we want to do this morning and we did not do. So let's say you have a pot. We have a pot, and let's do this radius is, what was the number I gave? 5 centimeters. Okay. Here this second radius right here, that is 10 centimeters. Okay. 10 centimeters. Then the medium is filled up to here height, which is, let's say, 15 centimeters. Okay, so let me change this. So here is a part. So we fill the medium all the way to the top. This is 10 centimeters. This is 5 centimeters, and this is 15 centimeters. So what is the volume of substrate? What is the volume of substrate? How do you calculate that? I told you this morning, right? Simple cylinder pi r square h formula, right? So why don't you do that and tell me the value? We'll get the volume of substrate. So 5 centimeters, 10 centimeters, 15 centimeters height, volume is equals to pi r square h. But what is that r? R is equals to r1 plus r2 divided by 2. What was that? 2650. What are the units? Centimeter cube. Okay, everybody got that number? 2650 centimeter cube. We'll give some time for everybody to finish calculation. Pi r square h 3.14 times r is 10 plus 5 by 2 7.5. So 3.14 times 7.5 times 7.5 times 15. Everybody got the numbers? 2650, do you all agree? Anybody got a different number? All good? So, okay, so we got this substrate volume. This is how you calculate substrate volume. Let's say I added 1000 ml of water into that pot, into that substrate, 1000 ml. So 1000 ml can be written as 1000 what? Centimeter cube, right? Same, ml is equal to centimeter cube. So now we want to calculate volumetric water content, okay? There is a symbol for this volumetric water content. The symbol is Greek letter theta, okay? Sure, we can take, you want a break? Yeah, yeah, no. All right, so they want, okay, all right, we can finish this and we'll come back in 2 minutes. So volumetric water content, VWC, volumetric water content, has got a symbol, Greek letter theta, okay, that's called theta, is given by formula, what formula? Substrate. So what is volume of water? 1000, right? 1000 centimeter cube divided by, what is the volume of substrate you calculated? 2650. 2650 centimeter cube. So what is the answer? 0.3, 0.38, 0.38 centimeter cube of water per centimeter cube of substrate. Okay, or this can also be written as percentage wise what? 38%, right? It can also be written as 38%. That is that number, percentage. Okay, that's that number. Okay, that's how we got that number. Then how do you get this number? For this number we need sensors. We have metric potential sensors, we put them in the soil and then they give you a value. So what you do is you take your substrate, whatever substrate you buy, and you artificially create different water contents. You create different water contents. You add 1000 ml in one part, 500 ml in another part, 2000 in another part, 2500 in another part. So you are now adding different amounts of water. And then for each part you measure volumetric water content using this formula. You get these numbers. But then in the same parts you put the sensor, metric potential sensor, and it will give you these numbers. So once you have these numbers and these numbers, you plot the graph. That's how you get to this graph. Okay? Alright, why don't you take a break and then come back here. Alright? Exposure, right? Come onto the stage. One of you. If you're not coming, I'm going to choose. Don't make me choose. It's alright, come on, you can come. One of you come, between you. It's okay, it's easy. We'll take care of the drawing. Come over here. Yeah, there you go. There you go. Appreciate her. So I have a picture here, right? Some sort of a plant, if you can assume that it's a plant. with some leaves, roots, stem. I have some numbers on the left side. I want you to take those numbers. You see those numbers? Yeah. I want you to put those numbers on that picture. So first of all, what are these numbers? These numbers are water potential numbers, right? Pressure of water, right? Now you have to select them, take them and put them where they should belong for water to move through the plant. Anybody wants to help her? Who is her teammate? No, not you. You're not a teammate. They are the teammates. Come on, both of you, come. Huh? That's cheating. Okay. You understand now? Why that? Can you explain why it is? Why do you want to keep the lowest number down here or highest number down here and lowest up there? To the lower potential. So why don't you erase the other numbers because it's confusing. You can click that eraser there, yeah, and then erase it. Okay, -1. Yeah, that's okay. Okay, so this is the normal situation, right? Now I want one of you to come on the stage and draw the scenario when there is drought stress. When there is drought stress, okay? The plants are experiencing drought stress. What is the scenario? What will be the numbers look like? Who wants to do that? There is drought stress. Okay, go ahead. Whoever is first, they can go up the stage. Do you want to go there? Go ahead. Okay, she raised first, so you have to wait.
You can try.
Plants are experiencing drought stress, so I want to see the numbers. How do they look like? I'm not going to tell you. You came here. You said you will do it, so you have to do it. So you can come up with any numbers. It doesn't matter. I want to know. I want you to draw a scenario where the plants are experiencing drought stress. How those water potential numbers will look everywhere.
So let's come to numbers.
So I'm confused. So what are your numbers? Maybe you can want to show me with an underline. Whatever numbers you wrote, just
So I
underline it.
have changed the potential of the root and soil risk. Now the root is on higher water potential as compared to the soil, so that they cannot uptake the water from the soil. Rest.
So so when this situation happens, yes, you're telling me that the soil now has less water because the number has become more negative. I understand that. But plants are not static. They are going to make some changes. Okay? Because if this situation prevails, what happens? There is no water uptake. Within a few hours, plants are going to wilt and die. So when there is drought stress, until you get to really bad levels of drought, the plants won't die, isn't it? So how are they able to cope up?
So they have certain physiological mechanism, like they'll reduce their photosynthetic and their respiration rates. Along with that, if there are any modifications, there might be some modifications to reduce the water loss from the plants.
So all of that is good, but there is one major thing they will do. Have you heard about osmotic adjustment? Anybody? What is osmotic adjustment?
So,
Osmotic adjustment. Anybody heard about that? Osmotic adjustment.
there is a movement of ions.
Sorry, one at a time. What's your answer? And we'll get to you. 1 second.
So
Think
movement
about
of
it.
ions, they produce certain osmolytes also in response to the drought stress. For example, in the severe drought stress, proline hormone is produced by the plants in response to that.
So what happens to those numbers? Do you have an answer?
Abscisic acid production increases.
Yes, but I want all of that in terms of those numbers. I want you to tell me a scenario. You're going away. No? Okay. You have an answer. Yeah, go and try. I want you to tell me how plants are going to look or what they're going to do to their water potentials when they experience drought stress. They are not going to remain calm and say, okay, I'm done, I'm going to die tomorrow. No, they're not going to do that. They are going to make some changes. And you said proline, this and that, abscisic acid. But what I want to know is how those numbers are going to change. What happens? So you may want to erase everything and maybe start if you want, if it is confusing. Anybody can help him. If you want to chime in, help him, help him. Okay?
Similarly,
If you want, you can work together. I don't need to know. I know the answer.
First we reduce the sulfur also.
So what has happened to soil? Soil has become more negative, right? So let's write that first. Okay, can plants change the water potential in the atmosphere? So that remains same, right? Now, water has to flow. Water has to flow, right? Now, for water has to flow through. I mean, it's less water. I get it, but still, plants will pull that water as long as they can. What can they do to make the water flow inside?
So we can even like the plant's roots will also lower potential.
Well, where will it start? You said proline, everything. Where are those things happening? Start at the leaves first. Osmotic adjustment. Osmotic. So what happens? What was the original number for the leaf? Now what will happen to leaves? When they, so this morning I think you asked the question, right? When you add salts to water, what happens to osmotic pressure? It becomes more negative. Water is bound by it. So you are saying that plants are going to create some salts, proline and this and that, osmoregulants. They get synthesized in the leaf. When they get synthesized in the leaf, what happens to that number in the leaf? From 1 point, minus 1.5, it changes to, well, it go, yes, because you are adding more salts. Salts will make it more negative. So they have to probably do minus 2.5. So when that is minus 2.5, then stem will become minus 2, not 2, 2.0. And then roots becomes minus 1.5. That is how they adjust. They are not static. They are very smart. So what they immediately do is, okay, there is no water in the soil. There's, yes, correct. There is no water in the soil. What can I do? I'm going to stop photosynthesis. I'm going to photosynthesize, but I'm not going to use those sugars to produce new leaves. I'm going to use those sugars to produce salts, proline, some other osmoregulants. They're all salts, and then fill those salts in the cells of the leaves. Therefore, all the leaf cells now become much more negative in their water potential. That same trend follows in the stem and in the root. Now all of a sudden water is flowing. There is less water, but is now still flowing into the root. That is called osmotic adjustment. And you just described osmotic adjustment using water potential numbers. That's all. Did everybody follow this? Does it make sense? Yeah, plants won't sit calm. Oh, it's over for me. I'm going to die tomorrow. No, that's not going to happen. They are going to do something, and in this case, that's what they do. Got it?
With the negative numbers, the thing is that we usually think the higher the number, the more potent it is. But with the negative number, it's opposite. For example, if it's minus 0.5, then if we go to minus 2.0, it becomes more potent in that case scenario. Not works like reducing the number, which we usually do in the positive numbers case. So that is what happening. If the soil is going to minus 0.5 here, the plant is adapting. The roots went from minus 0.5 earlier to minus 1.5, which is much more potent adaptation towards this change into the soil. And the similar is happening at the stem and the leaves as well.
And it's all because of those osmoprotection synthesis, biosynthesis of osmoprotection. Basically, biologically prepared salts. That's all. Okay? Cool. All right. 4:45. You have any more questions for me?
What are these osmoprotectants?
Those are secondary metabolites. Right, these are secondary metabolites. Proline is one of them. There are also several of them. They just get built up in the cells, and when they are building up in the cells, the cell has now much more negative water potential.
Will be having any charge on them?
No, they're just salts, simple salts, compounds. They're simple compounds which act like osmoprotectants. That's all. Same thing happens, that osmoprotection happens even under cold conditions. When there is a lot of cold, what happens is the cells can freeze. To stop that freezing, they synthesize these chemicals. So it's called supercooling. And basically inside the cells, the osmoregulation has happened and the cells won't freeze and the plant won't die. This is the mechanism the plants have. Okay. All right. I don't know what rapid fire questions you want to ask. You can if you want. He was proposing that he's going to ask rapid fire questions and he wants to test all of you, your knowledge from his questions. So go ahead, fire away, but you can also ask him if you want. Rapid fire questions.
So I was proposing that all the earlier topics which were covered, we can divide the class into the group of two, and then someone from the group comes and explains each topic one by one. So if someone misses on that, they lose a point, and we can rate who learns better.
But we got only 15 minutes,
Yeah.
right?
So that was earlier.
That was earlier. But if you want to do that in a better way, we can. You should come prepared for that, right? All of you should come prepared, so we give fair chance.
We can schedule it for
Yeah, we can schedule it for some time. Yeah, for tomorrow maybe, and then you can fight with each other. I don't mind. I'll sit and have fun. Yeah,
Sir, it can
watch.
also help in the revision of the topic.
Yes, yes, you can. Okay, and but then you have to choose people randomly. Meaning, we're going to write numbers on a paper.
You can choose the people.
Yeah, well, randomly. But you can choose all the people you want, but no, it should be random. The grouping should happen randomly. Okay, 2 groups randomly prepared. Okay, we can do tomorrow. All right, why don't you guys take off for today otherwise? Okay, and then we'll see you tomorrow. Do come tomorrow morning. Don't tell me that you're sick or something. No, I don't believe it. Okay, all right, go out. You can take off now.